Tonight's presentation is titled Diagnosing a Rough Engine. And our presenter is Mike Bush. Mike is continuing in his series of EAA webinars. Mike is the president of Savvy Aircraft Maintenance Management. He holds a certified flight instructor certificate with an A&P mechanic certificate, which includes the inspection authorization. Mike is an author for numerous aviation publications, including EAA's Sport Aviation magazine. Mike was honored in 2008 by the FAA and named the Aviation Maintenance Technician of the Year. Mike is a member of the EAA and volunteers his time to be with us once a month and put these webinar presentations together and deliver them to us. So we are very grateful for Mike taking the time, volunteering to share this information he has with us tonight. Mike, I'm going to turn control of the presentation over to you.
Good evening, everybody. Wow, it looks like there's almost 800 people in the room tonight, and it's still climbing. That may set a record tonight. I don't know, Tim. Any rate, so we'll get started. As Tim said, the subject for tonight is diagnosing a rough engine. Rough running engine is a common squawk that we often see reported by pilots and aircraft owners, and it's often a difficult kind of thing to diagnose because you know, if the roughness can be duplicated on the ground, then a mechanic might be able to troubleshoot it systematically, but most of the time it can't. Most of the time a rough running engine, unless it's really horrendously rough, can only be duplicated in flight, and if it can't be reproduced on the ground, it's very, very difficult for a mechanic to troubleshoot it in a systematic fashion, and the mechanic is generally reduced to using guesswork, which is always a bad thing. We call this shotgunning, and it can get pretty expensive and ugly. So we want to avoid getting into a shotgunning situation at all costs. Frequently we see that situations where owners report a rough running engine and mechanics start doing things like changing out fuel pumps and magnetos and other expensive components that, if you think about it, really couldn't possibly be the cause of the roughness. So it's important to think critically about the subject of engine roughness and sort of go back to first principles. What causes engine roughness? It turns out that a rough-running piston aircraft engine is a very specific symptom. And it's always, or almost always, due to a very specific reason. And the reason is that the cylinders aren't all producing the same amount of power. So if we start from that premise, and here's a picture of an actual rough-running four-cylinder Lycoming engine. Well, no, that's not actually a picture of a Lycoming engine, but you get the idea. If all of the cylinders are not producing the same amount of power, then that will be perceived as roughness. And if the cylinders are producing the same amount of power, the engine will be perceived as running smoothly. Now, it might have lost power, it might have other problems, but it won't be rough running. Rough running is a specific symptom that means that the different cylinders are putting out different amounts of power. So how could a faulty fuel pump, for example, affect different cylinders differently? How could a faulty fuel pump be responsible for an engine running rough? Well, the answer is it can't. But other things in the fuel system, like a clogged fuel injector nozzle, or maybe an induction leak, could affect one cylinder differently than the others. You know, similarly, how could a magneto affect different cylinders differently? And again, the answer is it can't. If a magneto has problems, those problems will affect all of the cylinders the same way. But a cylinder-specific ignition component, like a bad spark plug or a bad ignition lead or a bad contact spring, could affect different cylinders differently. So when we're trying to diagnose a rough running engine, we need to focus on components that could affect different cylinders differently. And we can pretty much rule out things that affect all the cylinders the same, like fuel pumps or magnetos or other things like that. And if you just capture that one concept, then an awful lot of the wasteful component replacement that we often see happen in the field can be avoided. And usually the quickest way to accurately diagnose a rough running engine is by dumping engine monitor data and analyzing it. And hopefully you have an engine monitor installed in your airplane, and if you don't, a couple of rough running engine episodes will pay for the engine monitor easily, because being able to analyze engine monitor data often makes the diagnosis very, very simple and very quick. And without engine monitor data, it's often quite difficult to identify the cause of the rough running engine. So to give you an example, if we suspect that the rough running engine might have something to do with an ignition problem, then we take the airplane up and we do an in-flight mag check, preferably one with a fairly lean mixture, which is kind of a worst case stress test for the ignition system. And then we take a look at the data and see what it tells us. This is an example of an in-flight mag check where it immediately is obvious, looking at this data, that when the engine was running on the left magneto, that orange trace, the number 5 EGT, goes unstable. And the number 5 EGT, the number 5 cylinder left mag fires the bottom spark plug in cylinder number 5. So we can be almost certain that the problem with this engine is a bad number 5 bottom spark plug. Also, when we look at this data, we'll notice that the EGT rises when we go to the right mag. It also rises when we go to the left mag, which is normal. But it rises more when we go to the left mag, which suggests that the two mags are probably not timed the same. There's a split timing situation, which in most engines would be incorrect, because the vast majority of piston aircraft engines, both mags are supposed to be timed exactly the same. So when we see a different amount of EGT rise between the left mag and the right mag, that indicates that we ought to go recheck the timing, because one of the two mags has got to be off of its timing spec. Another situation that we run into quite frequently is an engine that runs smoothly at rich mixtures, but starts getting uncomfortably rough when the engine is leaned out for cruise, and particularly if it's leaned aggressively, for example, operating Lena Peak, as so many people do nowadays. And if we have an engine where it's running smooth at a rich mixture and rough at a lean mixture, then the cause is invariably mixture maldistribution, which means that different cylinders are running at different air-fuel ratios. And when we lean the engine out, some of the cylinders start getting so lean that they lose power, and we have a situation where different cylinders are producing a different amount of power. And to visualize why that happens, here's a chart that shows plots EGT and horsepower as you move the mixture control from a rich mixture, which is over on the right side of the chart, to a lean mixture, which is on the left side of the chart. And if you look at the horsepower curve, notice how flat it is when the mixtures are on the rich side of peak. So a little change in fuel flow makes almost no difference in horsepower. But when we get onto the lean side of peak, and even as we get near peak, in fact, the curve starts to steepen. And so that when the mixture is lean, a little change in fuel flow makes a very significant change in horsepower. So if we have, and let me blow that up, so you can see it a little bit more clearly. So if we have, in this case, 6 cylinders that have a range of different mixtures, some cylinders are leaner, some cylinders are richer, which is normally the case. The aircraft engines almost never have exactly the same mixture in all the cylinders. And if we're on the rich side of peak, that difference in mixture has almost no effect on horsepower. So even though the cylinders are running at slightly different mixtures, they're putting out the same amount of power. When we pull the mixture control back to a leaner mixture and get onto a steeper part of the curve, then the fact that the cylinders are running at slightly different mixtures can have a very profound effect on horsepower. And the leaner cylinders will be putting out significantly less horsepower than the richer cylinders. And again, when different cylinders are putting out different amounts of power, that's when we feel that the engine is running rough. So if the engine runs smoothly when rich and starts getting rough when lean, it's almost always an issue of mixture maldistribution. The fuel flow difference between the richest cylinder and the leanest cylinder is what we call a gammy spread. And in order to get the engine to run smoothly at a lean mixture, we want to get the gammy spread as small as we possibly can. For the smoothest operation, Lena Peak, we generally attempt to get the gammy spread down to a ½ gallon an hour or less. And what that simply means is that as we lean the mixture and watch where each cylinder reaches peak EGT, the fuel flow at which the richest cylinder reaches peak EGT and the fuel flow at which the leanest cylinder reaches peak EGT should hopefully be within a ½ gallon an hour or less of one another. Again, if we have an engine monitor, we go up and do a quick flight test where we do a mixture sweep. Typically we do a couple of them where we move the mixture control from rich to lean and then lean to rich and do that several times. Then we dump the data and we analyze where the leanest cylinder peaks and where the richest cylinder peaks. In this particular case, number 3 is the leanest cylinder, and it reached peak at 13.4 gallons an hour. 4 was the next leanest, and 1, 2, 5, and 6 all tied for richest at 12.9 gallons an hour. The difference between 12.9 and 13.4 is a ½ a gallon an hour, which is an acceptable gammy spread. But if the fuel flow where the leanest cylinder peaks and the richest cylinder peaks was, say, a gallon an hour or a gallon and a half an hour, then we would expect that the engine would not be real happy running Lena Peak for the reason that we just talked about. If the gammy spread is greater than what we want it to be, if it's a fuel-injected engine, then that's a simple problem to resolve. We install a set of position 2 nozzles that are calibrated to each cylinder in order to make all the cylinders run at approximately the same mixture. And if the engine already has position 2 nozzles, then we may need to tweak a couple of them to get the GAMI spread down to where we want it. For carbureted engines, it's much more difficult because we don't have nozzles to tune. And typically, it's usually not possible to get a carbureted engine to have as tight a GAMI spread as a well-tuned injected engine. But there are a couple of things that we can do operationally that will help minimize the GAMI spread on carbureted engines. One of them is to avoid operating at wide open throttle. If we pull the throttle back just a little bit from its wide open position to cock the throttle butterfly, that causes the air passing through the carburetor throat to become turbulent, and that improves the fuel atomization and makes the mixture distribution significantly better. Another operational thing we can do, especially when it's cold out, is to use a bit of partial carb heat to warm up the air as it enters the carburetor, because again, warm air will atomize the fuel better in the carburetor. And when I say atomize fuel better, I mean that the size of the fuel droplets embedded in the fuel air mixture coming from the carb, the size of those droplets is smaller. And the smaller the droplets, the better they are able to negotiate the twists and turns of the induction system and reach all of the cylinders in the same proportions. So for carbureted engines, those two operational things will help minimize GAMI spread. And for fuel injected engines, tuning the fuel nozzles is the way we do it. But in any case, we want to try to keep the GAMI spread as small as possible, meaning that the cylinders are all operating at approximately the same fuel air mixture, as close to being the same as we possibly can. However, even if the GAMI spread is as good as we can get it, is very close to zero, we have to recognize that an engine will always run a bit rougher when it's leaned aggressively than it will with a rich mixture. And this is due to a phenomenon called cycle-to-cycle variation, or CCV. And this is an area where a lot of research has been done in recent years, because automobile engines nowadays all run aggressively Lena Peak in order to meet smog regulations. And so in order to get automobile engines running smoothly on very lean mixtures, an awful lot of research has been done on what happens in a cylinder when the mixture gets very lean. The term cycle-to-cycle variation, or CCV, refers to the fact that each successive combustion event in a particular cylinder is a bit different from the last one. There's a certain amount of randomness that happens in the combustion of the fuel air mixture, so that the combustion events, successive combustion events in a single cylinder receiving identical fuel air mixtures varies from one event to the next. And again, when cylinders are producing variable amounts of horsepower, we perceive that as roughness. And again, a lot of research has been done about why cycle-to-cycle variation happens, and it's really quite interesting. It turns out that the primary reason for cycle-to-cycle variation in a particular cylinder is because of what happens in the first couple of milliseconds after the spark plug fires. The spark across the spark plug electrodes ignites the fuel-air mixture in the immediate vicinity of the spark plug and creates what's called an early flame kernel. And that early flame kernel ultimately organizes itself into a well-defined flame front that burns across the combustion chamber during the combustion event. And the entire combustion event takes on the order of 20 to 30 milliseconds. But it's what happens during the very first couple of milliseconds after the plug fires that is primarily responsible for cycle-to-cycle variation. And that's because the formation of an early flame kernel is somewhat chaotic and has a lot of randomness to it. There are some fascinating photos that were taken in a special engine that was equipped with a piston that had a quartz window in it, so that it was possible to actually photograph what was going on inside of the cylinder with a very high-speed camera during those first couple of milliseconds after the spark fires. And here are some actual pictures of the development of an early flame kernel. And you can see that it is not it's not exactly a smooth event. It's, you know, we sort of have a picture that the plug fires, and then the flame starts from the spark plug and moves outward in a symmetrical fashion. But in fact, that's really not what happens. It's a very chaotic sort of development, as you can see from these photos. And sometimes the flame kernel organizes quickly, and sometimes it organizes slowly. And depending on what happens during that particular combustion event, the chaotic formation of the flame kernel can cause the flame front to develop a little faster or a little slower than it did the previous time the spark plug fired. And that creates small variations from one combustion event to another. And it turns out that that this variation from one combustion event to another is always greater the leaner the mixture, and is less when the mixture is rich. And I'll show you some actual data that illustrates that. But the reason that it's slower and more chaotic with lean mixtures is simply because a lean mixture is harder for the spark to ignite than a rich mixture. So the result of the spark plug firing becomes more and more unpredictable, if you will, as the mixture gets leaner and leaner. Now there's a second really interesting phenomenon that kind of aggravates or amplifies this problem of chaotic and somewhat random flame kernel nucleation. And that is that at the end of the combustion event, after the flame front has passed across the combustion chamber and the exhaust valve opens and the piston comes up to expel the exhaust gas, it's never possible for the cylinder to expel all of the residue of the previous combustion event out the exhaust valve, because it would require an infinitely high compression ratio for that to happen. So if you think about it, after the piston reaches top dead center during the exhaust stroke, there's still a certain amount of residue from that previous combustion event that stays in the combustion chamber and doesn't go out the exhaust. And so what happens is interesting. If a particular combustion event got a slow start because the flame kernel nucleated more slowly than usual, and the combustion event therefore progresses more slowly than usual, then at the end of the of that combustion event, the residual gas in the combustion chamber will have more unburned fuel in it than if that combustion event started quickly and proceeded more completely prior to the time the exhaust valve opens. And so if the combustion event got a slow start, there's going to be a little excess fuel in that cylinder during the next combustion event, left over from the previous one. And this phenomenon it tends to cause somewhat alternating high and low power production on successive combustion events. So it sort of aggravates this cycle-to-cycle variation. And this stuff is very complicated, very dynamic, and research into it really has been relatively recent, but there's been some really interesting stuff done, like those pictures I showed you. Here's a scatter diagram where the peak pressure in a particular cylinder was measured on 200 successive combustion events. And you can see how it's scattered. It's not the same every time. Sometimes the pressure gets higher, sometimes it's a little lower. And you can see that that if you do it with a lean mixture, the scatter is significantly greater, and there are more, specifically more outliers on the low side than when the mixture is richer, because of what we talked about, that the randomness of early flame kernel creation is greater when the mixture is lean than when it's rich. Here's another diagram, again showing peak pressure on successive combustion events, the rich mixture and lean mixture, and you can see that with the lean mixture there's more variations, and there's a number of quite low outliers where the cylinder produced significantly less power than usual during those particular combustion events. All of this stuff is perceived as an engine that's running a little bit rough. And finally, here's yet another diagram that's showing kind of the same thing, and showing that as the mixture gets leaner and leaner, the cycle-to-cycle variation gets greater and greater. Now this is pretty much baked into the cake in terms of operating Lena Peak, particularly aggressively Lena Peak. And we just have to live with the fact that there is a little bit more roughness when we run lean, because it's just the physics of the situation. Aircraft engines do a little bit better than car engines because they have 2 plugs in each cylinder, and that tends to cancel out a little bit of the variation. One thing that we can do to improve the cycle-to-cycle, or reduce the cycle-to-cycle variation a little bit, is to use fine wire plugs, which are more expensive, but they produce a somewhat more consistent flame kernel nucleation than massive electrode plugs. I use massives in my airplane, and I just accept the slight additional roughness. But if you want to get the engine running as smoothly as it possibly can with a very lean mixture, then fine wire plugs will help a bit. But that's pretty much, there's no way to avoid it altogether. It's just a fact of life that the leaner we run these cylinders, and of course the operational trend has been to run them leaner and leaner, the more of the cycle-to-cycle variation we're simply going to have to accept, just because of the basic physics of the situation. So Tim, that's all I have prepared. We can open it up for some Q&A if you'd like.
Great. Sounds good. Mike, we did get some questions in here, so I assume we'll get quite a few more in here, too. I was looking at the counter, and it's darn near up to 900 on the counter, so great turnout tonight.
I hope you can keep up with the questions.
Oh, boy. Okay, so let's
hope
see.
I can answer some of them.
Well, yeah, right.
We'll see.
Okay, question here from Mike. On the Richa Peak, Lena Peak scatter diagrams reflecting Pmax and manifold pressure, were those values at the same horsepower?
Yes, those values were at the same horsepower. That particular scatter diagram, those were at the same horsepower.
Okay. And Walt's wondering, are there any trends for cycle-to-cycle variation with respect to cylinder volume or RPM?
That's an excellent question, and I don't really know the answer to it. My guess is that, again, we probably suffer less cycle-to-cycle variation in our relatively slow-turning aircraft engines than we would in a high-revving automobile engine. I don't know that for a fact. It just sort of makes sense to me because the duration of the combustion event at a high RPM is much less. So a variation of a millisecond or so in nucleation of the flame kernel would make more of a difference at higher RPM. But I'm just reasoning that out from first principles. I don't actually have any data on that.
Okay, so David asked the question here. So can running Lena Peak, can it cause premature TBO?
No, we don't find that at all. Quite the opposite. When you run Lena Peak, and this is not something we were concentrating on tonight because the subject was roughness, but when you run Lena Peak, the pressure curve during the combustion event, if you track the pressure curve during the event, it's much broader and has a much lower peak than running a rich mixture. And so the instantaneous stresses on the power assembly components and the crankshaft bearings and all that stuff are significantly less when we're running Lena Peak than running Richa Peak. So actually what we find is that Lena Peak, assuming that it's done correctly, will actually help prolong the life of the engine rather than the other way around.
Cool. Ian's wondering, how do you tell the difference between spark plug problems and magneto problems?
Well, again, virtually all magneto problems are going to affect all of the cylinders. If you have a problem that only affects one cylinder, which is normally what we run into when we are dealing with a rough engine, then the problem is almost certainly not a magneto problem. It's almost certainly a problem with something that is specific to the one cylinder, most commonly a spark plug, occasionally an ignition lead. But the spark plugs are the things that operate in the hostile and filthy environment. So usually the spark plug is the first thing we look at, just because the probabilities of it being the culprit are much higher than any other ignition component.
Gotcha. A question from David. He says, I have a more or less 0.3 gallon per hour GAMI spread.
That's
However,
excellent.
Yeah, however, after further leaning to say 30 degrees Fahrenheit Lena Peak on the richest cylinder, the EGT temps become quite divergent. Is this a problem?
No, it's not a problem. And actually, I did a webinar on this titled "The EGT Myth" that's on the server, and David might want to go Google that one because it actually goes into considerable detail about why the EGT spread increases as you get far on the lean side of peak, and why it's not a problem. So it's a little hard to describe it without having some pictures. So I would suggest that he take a look at that webinar where we actually talk about that specifically.
Excellent. Lionel's wondering, you expressed the GAMI spread by fuel flow. Can it also be expressed as a difference between highest and lowest EGT?
No, it can't. And again, that webinar called the EGT Myth explains that, and explains why we're not looking to minimize EGT variation. We are looking to minimize the fuel flow difference between where the leanest cylinder peaks and the richest cylinder peaks, and those don't correlate with one another. They're totally different things. So in that webinar, I refer to it as the flat top myth. The flat top myth is that we want all the EGTs to be the same, and that's just not the case. That's not what we're looking for. We're looking for the GAMI spread to be minimum, not the EGT difference to be minimum.
Mm-hmm. Norman just is wondering, is an iridium plug considered a fine wire plug?
Yes, the modern fine wire plugs are made with iridium electrodes. Years ago, they used to be made with platinum electrodes, but I think nowadays they're all made with iridium electrodes.
Craig's just wondering, can dual electronic ignitions improve the Lena Peak smoothness compared to one mag, one electronic, and two magnetos?
I have to plead ignorance on that score. My experience is almost exclusively with certificated aircraft, and presently, with the exception of the Aerosant system, of which there are very few flying, there aren't any dual electronic ignitions that are approved for certificated aircraft. There's Electro-Air has an STC to replace one magneto with an electronic ignition, but we just don't have any experience with dual electronic ignition. And I shouldn't say we. I don't. I think there are probably quite a few dual electronic ignition configurations flying in experimentals, but I just don't have any experience with that, and I'm sorry.
Okay, Scott's wondering, what about an engine that only runs rough at 1 RPM? What would cause this?
Well, I mean, that sounds like it's some sort of a balance problem, and typically what we would do in a case like that would be to hook up a dynamic balancing equipment to the power plant and measure the vibration and determine what the frequency of the vibration is, whether it's 1 cycle per crankshaft revolution, or whether it's at half crankshaft speed, or if it's at 1.5 crankshaft speed. And once we find out what the frequency of it is relative to crankshaft speed, then we probably can figure out where it's coming from. I mean, for example, the combustion events occur at half crankshaft speed. The magneto turns at 1.5 crankshaft speed, at least on a 6-cylinder engine. I'm trying to remember what it does on a 4. But that's usually the first thing that we try to do when we have a vibration problem like that, that is RPM specific, is to hook up some vibration analysis equipment. Anybody who does dynamic balancing has the equipment, and figuring out what the vibration frequency is relative to crankshaft speed.
Okay, Richard's wondering, couldn't partial carb heat cause carb ice to develop?
Well, I mean, it could under aberrant circumstances. It's a really good idea to, in any carbureted engine, and particularly the ones that are prone to icing. Lycoming carbureted engines tend to be very carburetor ice resistant because the carburetor is bolted to the oil pan and runs hot. Engines with a remote mounted carburetor like the 0470 Continental, it's in the Cessna 182 and so on, it's famous for being a horrible engine for carburetor ice. And in engines that are prone to carburetor icing, it's almost mandatory to have either a carburetor air temperature gauge installed or a carburetor ice detector, an optical carburetor ice detector installed. And if you have a carb temperature gauge, you can always apply carb heat to get exactly the temperature you want. If you have an ice detector, then you'll get a very early notice if carburetor ice starts to form, and you can take remedial action. But again, Lycomings, at least stock Lycomings, there's some experimental Lycomings that are flying with what are called cold induction systems. But stock Lycomings tend to be very resistant to carburetor ice. But some engines, particularly things like the Continental 470, are very prone to carb ice, and you need to have instrumentation to avoid that.
A couple of questions here about a carburetor icing chart. Wondering if you would know where somebody could find a reference to a carburetor icing chart that they could refer to.
Oh, in terms of where the greatest susceptibility is to carb ice?
I believe that would be what they're referring to, yeah.
I'm pretty sure that there's one in I think that there's an FAA advisory circular on carburetor icing that has a chart like that, but I'd have to do a little Googling to find it. And I bet if you Googled carburetor icing with the site of FAA.gov, you'd probably find it. I'm pretty sure there's an advisory circular on that subject.
Okay, great. Joe's just wondering, why is it that when initially operating Lena Peak and then you reduce power while descending at the same mixture position, do EGTs tend to raise significantly? You want me to repeat that?
No, I
Okay.
understand the question. I'm not sure that that's generically true with all engines. He's saying when reducing power, EGT tends to rise instead of fall.
Mm-hmm. At the same mixture position.
Right. The only reason that could happen would be if the fuel system on that engine was such that reducing throttle leaned the mixture significantly, and that's typically not really supposed to happen. So I guess we'd have to investigate the specifics of what engine it is and so on. That's not a phenomenon that I'm familiar with.
Okay. Frank's got a question here. My engine exhibits popping sounds at low idle power.
Yeah.
I'm told that this sound is produced by unburned fuel igniting in the exhaust stack. I aggressively lean, but doesn't seem to make a difference. A low idle power doesn't seem to make a difference at low idle power. Engine runs fine at higher power setting. Engine never feels like it's running roughed, just a lot of popping.
Yeah, and that's not an uncommon situation. Here's the reason is that when you lean aggressively, it slows down the rate at which the flame front progresses through the combustion chamber. And if you lean aggressively enough and the flame front is slowed enough, then the exhaust valve will open before all of the combustion is finished, and there will still be some combustion going on as the contents of the combustion chamber goes out into the exhaust stack. And when you do have burning in the exhaust stack outside of the exhaust valve, you typically hear that as a popping noise. So richening the mixture would probably make the popping go away, or probably if it's a carbureted engine, pulling carb heat, which automatically richens the mixture because it's hotter air, would probably make the noise go away. If it's a injected engine where you don't have carb heat, then you probably need to richen a little bit to make that popping go away. But that's not an uncommon situation.
Okay. Barry's wondering, how can we determine the difference between engine roughness and some type of vibration issue?
Well, that's a good question. And generally, what I ask pilots to do to help diagnose that is to vary RPM in flight and see whether the roughness is focused at a particular RPM, in which case it's probably some sort of a resonance problem, or whether it is whether it continues at different RPMs, in which case it's probably combustion related. And also, again, one of the first things we want to do is take a look at the engine monitor data to see whether there's any evidence that one or a couple of cylinders are running at a different power than the others. If we can't, if everything looks like it's running at the same power in the engine monitor data, then we're sort of forced to conclude that it's actually not combustion related, and that it's probably some mechanical thing. And that, as I mentioned in the prepared stuff, in the absence of an engine monitor, it can be really difficult to troubleshoot this stuff. Being able to analyze engine monitor data is one of the most powerful tools we have to try to get this kind of stuff sorted out quickly.
And you have something on your website that would allow people to download that data, be able to kind of get a spreadsheet. Is that right, Mike?
Well, what we have a site called savvyanalysis.com, which allows data from virtually all both certified and experimental engine monitors to be uploaded and analyzed. It's a tool that parses the data and graphs it out for you, and it has a bunch of software tools that that help analyze the data, and the site is free. We also offer a service where you can upload the data and have it professionally analyzed, and that's not free. That's a subscription service. But the basic Savvy Analysis site that allows you to upload engine monitor data and analyze it yourself is a free site, and it pretty much accepts data from every make and model of engine monitor, both the certificated ones and the experimental ones.
Boy, that's great. That's a great service to have out there. Thank you for that.
Yeah, it's savvyanalysis.com is the URL.
Okay, Pete's got a question here. He says, in cruise I sometimes get what I would call a brief hiccup of roughness. Any explanation?
No, I mean that's a hard one. Again, if he has an engine monitor and can dump the data, then and the hiccup is long enough that it can actually be captured in the data, because different engine monitors capture data at different rates. Some of the more contemporary ones capture a sample every second. Some of the older ones don't capture but once every 6 seconds or something like that. So the hiccup has to be long enough that it can be captured in the engine monitor data. But if it is, we can usually figure out what caused it. But it rarely occurring intermittent problems like that are always the hardest ones to diagnose because they're very difficult to reproduce.
Yeah. Mark wonders, he says, on my 0360 with aftermarket fuel injection normally has a CHT difference of about 30 degrees between cylinder 3 and cylinder 2.
That's very good.
Would this be considered a normal spread? Sounds like it would.
Oh yeah, that's a very good spread. I'd love to have a 30-degree spread in my Cessna 310. Now that means that the cooling system is set up very, very well in that aircraft.
Great. Okay, Matthew's wondering, what about an engine that backfires after flight while taxiing at low RPM?
Well, engines very seldom backfire. What he probably is referring to is what's called after firing, which is that popping noise that the previous questioner was talking about. A backfire means that combustion goes back into the induction system the wrong way, and that very, very seldom happens. So I would be quite skeptical that he's actually having backfires happening. But if he's hearing a popping noise, it's probably an afterfire, which means that the combustion is occurring so slowly that it's still in process at the time the exhaust valve opens, and so some of it is occurring in the exhaust stack where you hear it as a popping sound. And again, if that's the case, the solution is to either richen the mixture, or if in this case it's a carbureted engine, applying carb heat should make it go away. I'm not sure we want to apply carb heat on the ground though, so most likely the best solution is to richen the mixture, or maybe turn on the boost pump if he has a boost pump. Depends on the airplane.
Ross just made a comment here about that. He's wondering if that low RPM popping could also maybe be caused by a leaking intake seal. Leaking intake seal on a normally aspirated engine.
Well, again, I guess we need to know whether this is only affecting one cylinder or if it's affecting all the cylinders. If it's only affecting one cylinder, then you're going to be looking for things like that would only affect a single cylinder. But without hearing the popping, it's a little hard for me to know what we're dealing with.
Sure. A couple comments here about that carburetor icing chart. Professor Paul Shuck says he has it on his website, which is avsport.org.
Oh, very good.
And also Mark says that it's on the FAA safety.gov website also. So
Excellent.
a couple places there where you could get that carburetor icing chart. Okay, let's see here. Question about dynamic balancing. Roger's wondering if you can't feel any noticeable vibration at any cruise setting on his 0540 Lycoming, would doing a dynamic prop balance do anything beneficial?
Well, you never know how beneficial a dynamic balance is until you hook the equipment up and measure the vibration. And frankly, you know, if the vibration is low enough, typically the strategy is that's really good. Let's not mess with it, and you just take the sensors back off and call it a day. But it's really hard to know how much benefit you're going to get out of a dynamic balance until you actually hook up the equipment and measure what the vibration is. Dynamic balancing isn't terribly expensive, and so it's probably worth doing once just to see what the vibration level of that engine is and whether there's significant room for improvement.
Okay. Comment here from.
Yeah, go ahead.
No, you got something to finish?
Oh, I was just going to say it's just impossible to predict ahead of time whether it'll be beneficial or not.
Just a comment here from Steve. He says that your most recent upgrade to the Savvy Analysis site, which allows people with Grand Rapids engine monitors to stitch together multiple components of a flight recording, he said it's really super.
Yeah, that's the Grand Rapids thing was sort of problematic because it would dump little pieces of a flight, and so we got a lot of requests for that, and we tried to respond to it. So I'm glad it's being appreciated.
Cool. Tom says on a plane that does not have an engine monitor. I'm sorry, on a plane that does have an engine monitor but no fuel flow monitor, is there any way to obtain a meaningful indication of the GAMI spread?
Yeah, it's just that if the engine monitor doesn't record fuel flow, then you have to do it the old-fashioned way, and you have to hopefully have a confederate in the right seat and who writes down what the fuel flow is at when each individual cylinder peaks, because the engine monitor won't record that, so you have to record it manually. It is necessary to have a fuel flow gauge in order to determine a GAMI spread, because obviously it's measured in terms of fuel flow, but it's not necessary to have an engine monitor that captures fuel flow. It's just very convenient to have one.
Bob just says, in a turbo normalized engine, should the GAMI spread be expected to be maintained that same 0.5 or less standard? He says, I find mine to be typically about 0.7 to 0.9 gallon per hour after multiple adjustments.
Well, we always try to get them down to 0.5 or less. My company manages about 10% of the Cirruses in the world, and a very significant percentage of those are turbo normalized, and we generally can get them to 0.5 or less by just doing a little tweaking of the nozzles. So again, I don't know specifically what turbo normalized engine he has and whether it's a problem child in some sense, but but generally there's no reason the turbo normalized engine should have a gammy spread any wider than a normally aspirated engine.
Okay, a question here from Darren. What engine monitor sampling rate is best for general flying?
Well, it depends on how big the memory is. Again, the recent vintage engine monitors that have lots of memory tend to sample at 1 sample per second, and in some cases even faster. The older ones that were built back when memory was expensive and don't have a lot of memory, if you sample really fast, the memory can't capture very many hours of flight. So, for example, with the JPI 700, which is a design back from the early 90s, I think, they have a relatively small memory. So the default sample rate is 6 seconds, but it's user programmable and can be set as fast as 2 seconds. So we generally recommend for people with the JPI EDM 700s, which there are tens of thousands of them out there, that for normal flying they leave it at the default of one sample every 6 seconds. But when they're going up for a test flight to do, say, an in-flight mag check or a gammy lean test or something, that they reprogram the sample rate to the fastest it can go for that particular flight, and then at the end of that flight set it back to the default. From an analysis standpoint, of course, the faster the sample rate, the better. We want the finest granularity that we possibly can. But for normal flying, you also would like to be able to, capture 20, 30, 40 hours of flying in memory before it starts scrolling off. So it's a trade-off.
Milton's wondering, do you find bad ignition wires can cause roughness?
Yes, absolutely. It's not nearly as common as bad spark plugs. So we always examine the spark plugs first. But if changing a spark plug doesn't resolve the problem, then the ignition lead would be the next suspect. And sometimes the leads go bad, especially if they're a little long in the tooth. Fairly often the contact springs start corroding and causing problems. So yeah, definitely bad ignition leads can cause engine roughness for sure.
Mark's wondering, do fine wire plugs last as long as the massive electrodes when operating Lena Peak?
They last about 3 times longer, in fact, but they cost about 3 times as much. So on a per hour basis, it's about a push. Unless you drop one on the floor, in which case you'd much rather drop a massive electrode plug than a fine wire plug. but yeah, the fine wire plugs are a lot more expensive, but they last a lot longer, and so they're about the same cost if you cost them out on a per hour basis. Fine wire plugs typically are good for 400 or 500 hours tops before the electrodes are worn to the point that they have to be replaced. And fine wire plugs commonly will go to 1,500 hours.
Dave wonders, how large of a split and cylinder head temperature is acceptable for smooth running engine?
Well, it doesn't really work that way because a split and cylinder head temperature, while it could conceivably be caused by a cylinder that's producing less power, is usually caused by either a poorly designed cooling system or a cooling system where the baffles or baffle seals are not in good shape and are letting air leak where it shouldn't be allowed to leak. So generally speaking, the the CHT spread between the highest and lowest is really not a measure of roughness. It's a measure of how good or poor the cooling system is. And again, can be a combination of design. Older legacy airplanes tend to have much less well-designed cooling systems than modern design airplanes do, and also a question of cooling system condition, specific, particularly the flexible baffle seals that sometimes get old and don't seal real well anymore, or maybe have been flipped backwards or something, causing cooling system leaks. So there's not really a good answer to that question as to what the maximum acceptable CHT spread is.
Okay, Barry's wondering, will an issue with engine valves potentially manifest itself as engine roughness?
It can. It's not very common. Of course, if you had a sticking valve, which we sometimes see in Lycomings, that could cause an engine to run rough, and it's very obvious when you look at engine monitor data. Typically, sticky valve syndrome in Lycomings manifests itself first in what's referred to as morning sickness, where the engine will run rough when it's first started up and it's cold, and then it will smooth out as the cylinder head temperatures come up to temperature. And most of the time, the owner complains about the morning sickness, and it gets resolved before we get the things deteriorate to the point where the valves stick in flight. There are also cases, and we see this mostly in Continental engines, where a valve guide will wear to the point where exhaust gases will get up through the exhaust valve guide and start to anneal the valve springs and cause the valves to close slowly. And if that gets bad enough, it can cause roughness. But it's not; those aren't very common situations, and we would definitely want to exclude the more common things like clogged fuel nozzles and bad spark plugs and stuff before we started looking for low probability causes like valves.
Mike's wondering, he says, after replacing the engine-driven fuel pump on a Cessna 350, while doing the fuel setup, the engine idles extremely rough unless the low fuel pressure is adjusted to 13 psi or above. TCM says it should be 7 to 8 psi. Any idea what might cause this? I don't know the reason for the pump replacement. It's a relatively new aircraft, still under warranty.
I've seen that problem, specifically with that series engine, and the problem generally is with the flow divider, which is the spider thing up on top of the engine that splits the fuel flow into 6 equal parts. The flow divider has a diaphragm and a spring in it whose job is to shut off the fuel flow when the fuel pressure gets low enough to give a nice clean cutoff when you pull the mixture control. And if the spring is adjusted a little too tightly, we can run into situations where the flow divider thinks you're shutting down the engine when you're actually at low idle pressure, and increasing the pressure above TCM spec will cause that problem to go away. And if it does that, it's probably a bad flow divider, and it might need to get changed out. I have definitely seen that problem happen for, and on that particular series engines.
James just is wondering if you could please review, again, kind of how to tell if a cylinder is running rough because of a fuel mixture problem or a spark problem.
Well, there isn't an easy rule for that. We have to do it by the process of elimination. But for example, one of the first things we do in a situation like this is go up on a test flight and do a lean in-flight mag check, which is a stress test of the ignition system, and do a gammy lean test, which involves just sweeping the mixture from rich to very lean and back to rich again a couple of times, and looking at the engine monitor data. And if we see anomalies during the in-flight mag check, then we can be pretty sure that we're dealing with an ignition-related problem. If we see a larger than acceptable gammy spread, then we can be pretty sure that we're dealing with a fuel system problem, like a partially clogged nozzle or something like that. So the answer, at least as to how we generally deal with it, is that we start out doing a test flight. We have a set of test flight profiles that we ask the pilot to fly on that test flight. Those test flight profiles are, by the way, are on the Savvy Analysis site as a PDF file that you can download if you're interested. And then we dump the data and look at it and look for anomalies during the in-flight mag check and look for anomalies during the gammy lean test. And that generally will tell us whether it's ignition-related problem or a fuel-related problem.
James is wondering how much of a roughness factor is compression variance between cylinders, cylinder head compression. Can you diagnose if that's the main culprit with roughness?
If you're talking about differences in differential compression readings, like some cylinders at 75/80 and some cylinders at 62/80, the answer is you literally cannot tell the difference. There is no correlation at all between compression readings and cylinder power output. That's been demonstrated repeatedly in the test cell. Obviously, if the compression was 0 or something, then there would obviously be a big difference. But in terms of acceptable compression, say between 45/80 and 75/80, you literally cannot tell any measurable difference in horsepower. So there's no correlation at all.
Gotcha. Mark's just wondering, have you ever seen a pitted cam cause engine vibration at cruise?
It can, but it has to be really, really wasted. The cam lobe has to be almost non-existent. The toe has to be just about gone. We have seen bad camshafts, particularly on Lycoming engines, which tend to have more cam and lifter problems, where the cam was worn to a breathtaking degree, and the pilot never noticed the slightest difference in performance or smoothness or anything. So while a bad cam can cause roughness, it has to be really, really bad. And by the time it gets that bad, it would be astonishing if you hadn't found, ferrous metal in the oil filter and stuff like that would cause that cam to be taken out of service before it got quite to that point.
All right, Jim's wondering, when you clean and test a spark plug and notice that during pressure tests the spark is not as robust as the other plugs, could this cause noticeable roughness?
We talking about testing plugs in a bomb tester or something? Is that? I wonder
Sounds
if,
like it, yeah.
yeah.
Under pressure.
Um, it could. I have a lot more faith in the results of an in-flight mag check than I do bomb testing spark plugs. But if a plug looks really funky in a bomb tester, it probably ought to be retired. And certainly a marginal plug can definitely cause roughness. That's one of the most common causes of roughness are bad spark plugs.
Good to know. David is just wondering if a fuel flow can accurately be measured for a carbureted engine.
It can be measured accurately. Because the fuel going into the carburetor float bowl tends to oscillate as the float as the bowl level varies and the float goes up and down, opens and closes the needle valve. When you install an engine monitor with fuel flow on a carbureted engine, you configure the engine monitor and tell it that it's a carbureted engine. And what the engine monitor software does when it knows it's a carbureted engine is it puts a big low pass filter on the fuel flow to filter out those short-term fuel flow oscillations that are generic to carburetors, so that the fuel flow that's recorded and that's presented on the instrument is steady instead of oscillating. So you can get accurate fuel flow information on a carbureted engine. You just have to filter the data, and engine monitors are set up to do that. The software, configure the software to tell it that it's carbureted or injected, and it changes the time constant on the filter that it filters that data with.
Cool. Mark's wondering what could cause an engine that generally peaks at 10 gallons per hour to suddenly start to peak at 8 gallons per hour instead?
Good question. I wonder if it's an instrument error. One possible cause, I suppose, would be if the airplane went into maintenance and somebody retimed the mags and they were either off before and are correct now, or vice versa. But retiming the mags could certainly change where peak EGT occurs. Although a 2 gallon an hour difference is an awfully huge difference. I'd be a little skeptical of that. I guess I'd need to have some more data about that to try to troubleshoot it, because that's a very big difference.
Roger is wondering if do internal spark plug resistance variations have any significance on engine roughness, or is this simply a plug manufacturer's marketing?
No, it's a real problem, and it's a problem with champion plugs, and because of the kind of resistor they use. And we recommend that if you use champion plugs, that every time the plugs come out for cleaning and gapping, that the resistance is measured. The nominal resistance of a plug is about 1,500 ohms, and we recommend tossing any plug that measures more than about 5,000 ohms. And I've personally seen champion plugs that measured hundreds of thousands of ohms, even megohms. So it is a real problem. It's not just marketing hype. And we've actually seen champion plugs with high resistance that destroyed slick mags, because the plug had such high resistance that the mag crossfired inside the distributor, because that was the path of least resistance for the electricity, rather than to pass through that very high resistant spark plug. I've never seen it destroy a Bendix mag because they're larger, physically larger, and it's harder for them to crossfire. But I've seen a number of cases where slick mags got destroyed by a high resistance champion spark plug. I personally use Tempest plugs because they don't have that problem. But if you use champion plugs, it's just a good idea to measure their resistance, and if the resistance gets out of tolerance, to discard the plug.
Tyler's wondering, is there anything as a pilot that can be done to treat an in-flight rough-running engine on a fuel-injected engine?
As a pilot?
Yeah, if you're flying it, suddenly gets rough in flight.
Well, the first thing to try to do is to richen the mixture, because as we discussed, there are quite a few problems that can cause roughness, where the roughness occurs only when the mixture is lean and not when it's rich. Anything having to do with uneven fuel flow, like clogged injectors or an induction leak or whatever, the engine would run much smoother with a rich mixture, a richer mixture than with a leaner mixture. So if you're flying and the engine starts getting rough, that's certainly one of the first things to try, is to go to a richer mixture and see if that smooths it out.
Great. A couple comments here from folks about your manifesto book, and Larry says that thanks for the manifesto book. It's a good refresher book for use by us old timers.
Well, good, thank you.
David has a question here. He's wondering if, in your opinion, the Alcor probes seem to be more sensitive and durable than others shipped with some of the other monitors.
Actually, my own experience is that the JPI probes are the most durable I've seen. I've had more Alcor probes go bad on me than JPI probes. I don't know. That's anecdotal data. That's certainly not scientific data. But I've personally been very impressed with the longevity of the JPI probes.
Matt's just wondering, how do you clean your Tempest fine wire plugs?
Well, you clean them in a well, I was going to say a sandblaster, but it's not really sand that's used. It's a plastic beads that are used. But plug cleaners or plugs are cleaned by blasting them with an abrasive. And I think the abrasive of choice for spark plugs are small plastic beads. You can buy a bag of it from Aircraft Spruce or whatever.
Okay, and
they actually have a nice, Spruce actually sells a fairly inexpensive plug cleaner, and I'm pretty sure the one I use is one I bought from Spruce, and it's not very expensive and it works quite well.
Fabrizio's wondering, how can we recognize an engine roughness issue to carburetor ice?
You probably can't. You know, again, if you have a carb temperature gauge or an ice detector, then you can detect either ice formation in the case of an ice detector or the conditions conducive to it with a carburetor temperature gauge. But if you suspect that there might be carburetor ice, obviously you want to pull for full carb heat on. And if the engine suddenly gets rougher and then smooths out, you know it was carburetor ice.
Gotcha. Dwayne is wondering, would mag timing disparities show up during the pre-flight mag check?
Well, they could, in the sense that if the amount of EGT rise when you switch to the left mag and you switch to the right mag is significantly different, that generally is indicative of the fact that the timings aren't the same. We prefer the in-flight mag check as a more dispositive test, but you can compare the RPM, not the RPM rise, the EGT rise during the ground mag check that you do, and if the rise is significantly different between one mag and the other, then that almost always means that the mags are timed differently, and normally they shouldn't be timed differently.
Donald's just wondering, is there an optimum carb temperature for lower GAMI spread in a Continental 0470?
I can't really answer what the sweet spot is as far as carb temperature. That is a good question. I wish I had a good answer for it, but I don't.
Question here on somebody who has, Jack has a Stinson. He's got 165 Franklin on there. And he said the engine got rough one day. An airborne mag test showed a smooth engine on the left, a rough on both, and a very rough on the right. He said he pulled the mag, had it tested, and it would only spark a gap of ½ inch on cylinder 5, but 1 inch on the others. He said that replacing the mags solved the problem. So with that, Mike, it looks like we've reached the end here of our time. It was a good question and answer session. A lot of tough questions here came in tonight with this Diagnosing a Rough Engine webinar here. I sure do appreciate you tackling them and giving us this information tonight. Would you like to make some closing comments to the folks out there still listening?
Okie doke. Just highlight the next few webinars that I'm going to be doing first Wednesday of each month as usual. February we're going to be talking about ferry permits, when you need one, how to get one. On March 4th we'll be talking about cam problems. Somebody brought that issue up tonight. And on April Fool's Day, the webinar is called The Decision Point, and it really discusses how owners and IAs need to work together during an annual inspection. And so those are the next 3 that we're going to do. And just to remind everybody that you can sign up for the monthly free Savvy Aviator newsletter, email newsletter. Either by going to savvyaviator.com and signing up, or I think there's a checkbox on the survey that Tim is about to bring up at the end of the webinar. And if you're interested in taking a look at my book called Manifesto, which is basically a maintenance philosophy book, I guess you'd call it, it's on Amazon, and if you Google Mike Bush Manifesto, it'll take you right to it. So I encourage you to look at that if you're interested. And with that, Tim, I think we'll call it a wrap.
Great. Question for you about signing up for the newsletter. If somebody is already subscribed and receiving it, should they still be checking the yes box, or should they just ignore that question then?
Oh, you can ignore it, but if you check it, you won't get 2 copies. We're smart enough to eliminate duplicates, unless you give 2 different email addresses, and then you get 2 different copies.
Great, wonderful. Thanks for the clarification, sir, and thank you so much for the webinar tonight. And to all the attendees, thank you so much for tuning in tonight. Have a great night, everybody.
Good night, everybody.